Now that we have reviewed exponential functions and log functions, we are going to start looking at how to take the derivative of log functions in this lesson. And our focus is going to be on the natural logarithm, which is going to be base e. So the rule is, if you take the derivative of the natural log of x, that would be 1 over x. Please keep in mind that this works only if you have x here. If you have some inner function, like 3x or 2x squared, then you'll have to also additionally apply the chain rule. So in the first example, we have a function defined as 7x to the third times the natural log of x. And the first part of this question is to find the derivative. So we have a product here. We have 7x to the third as our first factor and natural log of x as our second factor. So we are going to apply the product rule here. And when we come down here and start looking at taking the derivative, I want to take the derivative of the first factor, so that would be 21x squared, times the second factor, which is natural log of x, plus, now we're going to multiply it by the first factor, which is 7x to the third, and multiply it by the derivative of the second factor. Now this is what's new. When we take the derivative of natural log of x, we get 1 over x. When we start simplifying this, when we multiply these together, we get 21x squared. When I multiply this together, I have 7x to the third over x. So one of the x's gets canceled out, and we're left with 7x squared. I would be fine at this point if you left it like this, but the author of the book chose to take it a little bit further and factor. So he factored out a 7x squared. So this is the derivative of this function here. Now we want to find the equation of the tangent line at x equals e. So we first need to find the slope of the tangent line when x is equal to e. So we need to plug in e into our derivative to find that instantaneous rate of change. First, we're going to find the corresponding value of y when x is e, because we're going to need that for finding the tangent line. So when we plug e into our function to find the corresponding value of y, we get 7e to the third natural log of e. So that's up here. So 7, and then e goes in for x, so we have e to the third times natural log of e. When we simplify this, we get natural log of e. We know that that's just 1, so we're left with 7e to the third. That's this. And then if you want to take it further, you can approximate it using your calculator as a decimal. I personally would leave it as exact and wait to round at the very end. So now we know that we have this point on our function, and this is the point in which we need to find our slope. We need to plug e into the derivative so we can find the slope at x equals e. So when we plug in x equals e, we have 7e squared times, using the factored form, 3 times the natural log of e, this is where we're plugging in the e, and then plus 1. The natural log of e is just 1, so we have 3 times 1 is 3, plus 1 is 4. So now we're going to have 28e squared. So now to find the equation of the tangent line, we know the point on the function. We know the slope. This was approximated using a decimal. And so using point slope form, I plug in my y1 and my x1. This is the point on the line, so this is what we're going to use for x1 and y1. So e goes in for x1, and 140.6 goes in for y1. And then the slope is 206.9. Now, when we expand this and add 140.6 to both sides, we will have our slope-intercept form. So this is point slope form. This is y-intercept form. So this would be the equation of our tangent line. Either one of these would work. Now let's look at what happens when you have an inner function. So when you use the chain rule with the log function, if this was just x like we saw at the beginning, then this would just be 1 over x. If you have a function inside that's not x, then you're going to write 1 over whatever this inner function is here, and then multiply it by the derivative of that inner function. And this is where you would use the chain rule. Now, this works for any log function. In fact, we don't even really need that first equation. Let's go back up and look. We don't even really need this, because if we apply the chain rule to this, we're going to get the same thing. So go back down. If I assume that this is x in here, this would be 1 over x times the derivative of x, which is just 1. So I would have 1 over x times 1, which is 1 over x. So you can just use this anytime you see a natural logarithm. Okay, so let's take a look at finding the derivative for this natural log function. Here we have an inner function, so we certainly need to use the chain rule. The derivative of any log function is 1 over whatever this is inside here, and then multiply by the derivative of that inner function. So the derivative of this function here of natural log 5x squared plus 2x minus 7 is going to be 1 over the inner function times the derivative of the inner function. Now, when I take the derivative of this, I get 10x plus 2, and when we multiply, I get 10x plus 2 over 5x squared plus 2x minus 7. In example 3, we're going to look at different ways that we can take the derivative of this function. One way is by using the chain rule twice, and the other way is by using the properties of logarithms. So in this first method, that's what we're going to use first. So we're going to use the properties of logarithms. So because this has an exponent here, using the properties of logarithms, I know I can bring that down in front. So before I start taking the derivative, I'm going to rewrite this using properties of logarithms. So I'm going to take the 3 down in front, that's going to go here, and then I take the derivative of this now. So I'm just carrying down the constant that was the exponent, and now I take the derivative. So when I take the derivative of the natural log of x squared minus 4, that's going to be 1 over that inner function times the derivative of that inner function. The derivative of this inner function is 2x. And then when we simplify that, we have 3 times 2x, so that gives me the 6x. And then we have x squared minus 4 in the denominator. Now, when we use the second method, we're not going to simplify first using the properties of logarithms. We're just going to find the derivative without any simplification first. So when I take the derivative of a log function, it's 1 over whatever this inner function is. So that's what we have here. And now I have to take the derivative of the inner function. So this gets carried down, that's done. But now we have to take the derivative of that inner function. This is where we can use the power rule. The 3 comes down in front. This gets decreased by 1. And now I have to use the chain rule again because we have this inner function when we use the power rule. So then I multiply by 2x. The 2x is the derivative of x squared minus 4. Now when we simplify this across the top, I have 3 times 2x, which is 6x. And then I have x squared minus 4 quantity squared. And that's all over x squared minus 4 all raised to the third power. I can get rid of two of these on the top and the bottom. I have a factor of x squared minus 4 on the top and the bottom. And in fact, I have two of them in common on the top and the bottom. So when I get rid of those two factors, I'm only left with one in the denominator. So my final answer is 6x over x squared minus 4. And as you can see, they come out the same. So the point of this is that just to remind you that there are different ways to take the derivative. There's always different ways to take it. You need to find what's comfortable for you. As long as you are following the rules of derivatives properly, then either way you're going to get the same answer. Okay, looking at example 4, now we're going to be using the chain rule, but the inner function is a log function. So when I take the derivative, using the power rule, the 4 comes down in front, and then that gets decreased by 3. So that's this right here. But because we have an inner function, we have to multiply it by the derivative of the inner function. So the derivative of natural log of 3x is 1 over 3x. This goes in the denominator. And then I have to multiply by the derivative of what's inside using the chain rule. So that would be the derivative of 3x. And then when we carry it down and we actually find the derivative of that, that would be 3. So this is our answer unsimplified. When we clean it up, these 3's can be crossed off. So I'm left with 4 times the natural log of 3x cubed over x, because these canceled out. In example 5, we have a quotient. We have 6 over natural log of 8x squared. There are two ways to do this. You can use the laws of exponent rules and bring this up in the numerator with an exponent of -1. Or you can use the quotient rule and keep it the way it is as a quotient. I recommend that you try it both ways so that you can practice and verify that you get the same answer. The author of the book chose to use the exponent rules to simplify it first. So now we can use the power rule and the chain rule. So when we take the derivative, when it's in this form, I bring the -1 down in front, and then I have to decrease that by 1. So I have the -1 in front times 6. This becomes a -2, but then I have to take the derivative of what's inside. Because we have two inner functions here, we're going to have to use the chain rule twice. I have this inner function, and then I have this inner function here, the 8x squared. So first we're going to break this down where we take the derivative of what's inside, which is the natural log of 8x squared. So this would give me the derivative of 1 over the inner function times the derivative of the inner function. All of this just gets brought down. So now I have to take the derivative of the 8x squared, which gives me 16x. Everything else gets brought down. This is our answer unsimplified. When we simplify it, we're going to get -12 over x times natural log of 8x squared quantity squared. This 8 and this 16 simplify so that if I divide both of them by 8, this becomes a 2. And so then I have 2x. So then I have 2x times -6 on top. That gives me -12x. And that x with the x squared in the denominator cancel. So I'm only left with 1x in the denominator. And then because this is an exponent that's -2, we bring that back downstairs to make it positive. one last example where we're going to use implicit differentiation that involves natural logarithms. So here is our equation. We're going to use implicit differentiation. So this is going to be a product rule because we have this factor and this factor. So when I take the derivative of this first term here, I take the derivative of the first factor, which is 12x to the third, times the y squared. Then we're going to add that to the derivative of y squared times 3x to the fourth. Here's my 3x to the fourth. Here's my derivative of y squared. The 2 comes down in front. My exponent decreases by 1, but because y itself is a function of x, we are going to write here times the derivative of y. So this is using the chain rule. Now when I take the derivative of the natural log of x, that's going to give me 1 over x. And when I take the derivative of 2 natural log y, it's going to be 2 times 1 over y, because it's going to be 1 over whatever this is, times the derivative of y, because this itself is a function. We've got to use the chain rule and multiply by the derivative of y. Now, when we clean this up a bit, we get 12x to the third y squared plus 6x to the fourth y times y prime plus 1 over x plus 2 over y prime. And then, of course, we have equals 0 over here. So now that we have this all cleaned up, our last step is to solve for y prime. So anything that has a y prime in it, so that would be this term here and this term here, should stay separate from the terms that don't have the y prime in it. So we're going to separate. So y primes go on one side and then everything else on the other. When you do that, these are the terms with the y prime, so we're going to keep them there. But the terms that don't have the y prime, we're going to subtract to both sides. Now that we have the terms with y prime in it separated, we can factor out the y prime and then divide by what's left over. So now I have y prime times this factor is equal to, and then these are the terms that don't have the y prime in it. And now we can just divide both sides by this to solve for y prime. So the derivative of y is going to be negative 12x to the fourth times y to the third minus y all over 6x to the fifth y squared plus 2x quantity. So here are your conceptual questions. So after you practice your homework, I suggest that you try to answer these and see if you understand the section.